Okay, so my name is Joe Belvicino, and I'll be covering midterm problems 4 and 5 from midterm 1. Really quick, I just want to cover some quick terminology that I have in the following papers we're going to go over. This sign right here means therefore, so imagine it as if it were a sentence. Therefore, this will happen, or therefore that will happen. ST, abbreviated, means such that. It's exactly how it sounds in English. I just abbreviate it so I can save space. And then this little box right here is called a tombstone, and it basically just means that the argument or the proof that I'm covering right now is finished. Okay, so let's move on and let's get started with problem 4. Okay, so we're tackling number 4 now, which is this question right here, which is let A and B be n by n matrices. Suppose A is invertible, but B is not. Prove that rank of AB is less than the rank of A. Okay, so in order to tackle this question properly, we need to have a few definitions in mind first. The first definition is rank, the maximum number of linearly independent columns of a matrix. Now, keep in mind that linearly independent columns means that you cannot write these columns as linear combinations from the other columns of the matrix. So basically that means that the different vectors that make up a matrix can't be turned into another vector within that matrix. The definition of an invertible matrix. So we have here A times A inverse is equal to A inverse times A, which is equal to I, which is the identity matrix. Invertible matrices cannot have linearly independent columns, and the reason for this is because an invertible matrix only has one unique invertible solution, in this case being A inverse. If you have linearly dependent columns in a matrix, you can have technically more than one solution, and that goes against the very definition of an invertible matrix. So keep in mind that invertible matrices need to have a unique inverse. And finally, we have here the definition for linearly dependent. So like we mentioned earlier, linearly dependent columns could be columns that can be construed as, linearly dependent matrices could be matrices that have vectors in them that can be construed as linear combinations of other vectors within that matrix. Another way of looking at it is that linearly dependent matrices are matrices that there exists some non-zero vector such that when you multiply that matrix by that non-zero vector, it equals to 0. For linearly independent matrices, you would have to have the 0 vector in order to have this happen. Okay, so now let's move on to the actual proof. So let's note that because B is non-invertible, it is linearly dependent, as per our definitions mentioned above. Therefore, a non-zero vector exists, x, such that when you multiply the matrix B by x, you end up with 0. Now, if we multiply the product of AB, so the two matrices mentioned above, by this vector x, we can write it as this. AB times x is also equal to A times the product of B times x. And the reason why we can do this is because of the associative properties of matrix multiplication. Now, we know that B times x on its own is equal to 0. So we know that A times the 0 vector is also equal to 0. Therefore, the multiplication of AB times this non-zero vector is equal to 0. Now, what is the significance of this? Well, when multiplying AB by x, we have the 0 vector. However, you can note that x is a non-trivial non-zero vector. Therefore, by the definition of linear dependence, AB is linearly dependent. Therefore, AB must also be non-invertible. Now, remember that what rank means. Rank is the number of linearly independent columns. Since A was completely invertible, that means that all of the columns within A were linearly independent. But because AB is non-invertible, this basically means that the rank of AB is less than the rank of A, meaning that there are more linearly dependent columns in AB than there are in the matrix A. Therefore, we prove the claim above that rank of AB is less than the rank of the matrix A. All right, and now we're going to move on to question 5. Okay, so now we're going to tackle number 5, which is true or false. There are 6 claims on number 5, so we're going to evaluate each claim, and then we're going to tell whether or not each one is true or false. So the first claim here is there exists an invertible n by n matrix A for which A squared is equal to 0. Now, in order to tackle this, let's remember exactly what it means to be an invertible matrix. So note that the definition of the invertible matrix is that there exists some matrix A inverse such that it is unique and such that A times A inverse is equal to A inverse times A, which is just equal to the identity matrix. Now remember that the identity matrix is just the n by n matrix that is composed of ones diagonally. So we can use this fact to tell whether or not A squared can equal 0. So let's proceed by multiplying A squared by A inverse on both the left side and the right side over here. So now we have the equation A inverse times A squared times A inverse, which is the same thing as saying A inverse times the product of A times itself times A inverse, which by associativity we can write out as A inverse times A, and the product of that times A inverse. Now, we know from our definition above of an invertible matrix that A times A inverse is equal to A inverse times A, which is just equal to the identity matrix. So what we end up with here is that A inverse times A and A times A inverse are both equal to the identity matrix. So the result here of A inverse times A squared times A inverse is just equal to the identity matrix squared, or the identity matrix times itself. So now what we have here is a contradiction. So remember the claim above. The claim above said that there exists some invertible n by n matrix A such that A squared is equal to 0. If we claim that A squared is equal to 0, we can plug in A squared into the above equation. Now, we can see here that A inverse times A squared times A inverse must equal the identity matrix squared, which is a non-zero matrix. However, if we plug in 0 in the place of A squared, if we set A squared equal to 0, A inverse times A squared times A inverse must also equal 0 by the properties of multiplying by 0. So basically what that means here is that it cannot equal the identity matrix if A squared can equal 0. But we know that for any invertible matrix, A inverse times A squared times A inverse is equal to the identity matrix squared. Therefore, we know that the matrix A times itself, so A squared, cannot equal 0. So here we can find that this claim is false. Now, something to keep in mind is that more generally, two invertible matrices multiplied together will produce a non-zero matrix because multiplying two matrices with all linearly independent vectors, which, if you remember from problem 4, was a definition for invertible matrix, will produce another matrix with all linearly independent vectors. This is a general rule to keep in mind. The justification for this rule isn't really important to go into right now, but it's an important tip to keep in mind whenever you're dealing with matrices that are composed entirely of all linearly independent vectors, or even matrices that are composed entirely of linearly dependent vectors. Okay, so let's move on to claim B. If A is an invertible n by n matrix, then for all vectors B in Rn, A of x equals B has a unique solution. Okay, so remember again the rules of invertibility, that there exists some unique matrix A inverse such that A times A inverse is equal to A inverse times A, which is equal to the identity matrix. Yeah, sorry, I lost focus of the camera there for a second. Now, if we multiply A inverse by A times X, we have the following. A inverse times A times X, which we know from above, on the claim above, is equal to A inverse times B. Now, we know that A inverse times B is just equal to X, or the identity matrix times X, which is the same thing. So we know that X is equal to A inverse times B. Now, keep in mind that A inverse here is a unique matrix. So basically, for every single B inside of the space, we can see that multiplying by this unique matrix A inverse will result in another unique vector. This is primarily because A inverse is linearly independent as per the definition of an invertible matrix. So we can evaluate here that this claim is true. Okay, now let's move on to C. Oops, sorry, spoiler alert. Okay. If A and B are invertible n by n matrices, AB is invertible. Now, let's note our statement from earlier. Invertible matrices are all linearly independent vectors, and multiplying invertible matrices will produce a matrix consisting of linearly independent vectors. We talked about that general rule above for claim A. So because multiplying n by n matrices produces another n by n matrix, we satisfied the requirements for invertibility. So basically what this means is that we have two matrices that are composed entirely of linearly independent vectors. And because they are both n by n matrices, when you multiply them by each other, you produce another matrix that is also n by n, and that is also linearly independent. And both of these requirements are necessary to have an invertible matrix. So what ends up happening is that you create another invertible matrix. Therefore, this claim is true. In order to illustrate this claim further, we can just show a quick mathematical proof here. So let's take two invertible n by n matrices, AB, and take the inverse of that, which is equal to B inverse times A inverse. And then let's multiply that out. Let's multiply that by AB on both sides. So we know that AB times AB inverse is going to be equal to the identity matrix. Note, however, here that we can also go ahead and rearrange B inverse times A inverse to be multiplied by AB. And if you were to do that, you end up with the identity matrix in the middle. So we end up here with B inverse times A inverse times A times B. And we know that A inverse times A is just equal to the identity matrix as per the definition of an inverse from before. So now we end up with B inverse times the identity matrix times B, which is just the same thing here as B times B inverse, or B inverse times B. So because these matrices multiply out and they become the identity, we can see here that the inverse AB times the original matrix AB are all equal to each other. So, or will equal out to, when multiplied, will equal out to the identity matrix. So basically what the situation here is, like I mentioned before, when you multiply two matrices that are n by n and are linearly independent, which are the prerequisites for an invertible matrix, you produce another n by n matrix that also is consistent of linearly independent vectors. Okay, now speeding along, we're going to D. So we're already claim 4. We're halfway through. So the claim is the two vectors v1, which is equal to 1, 1, 0, and v2, which is equal to 1, negative 1, 0, form a basis for the subspace spanned by the vectors 1, 0, 0, and 0, 1, 0. Okay, so there's a lot of terminology here. So let's get our definition straight again. Right. So the definition of the span, the set of all linear combinations of vectors in some vector space Rn. So basically, this is the set of vectors that can be produced by a specific set of linearly independent vectors, which moves us to our basis. So the basis, think of the basis as the general seed or the set origin of a span. And what a basis is that it's a set of linearly independent vectors that spans some space Rn. So basically, it spans a certain amount of dimensions in a certain vector space. A basis can be used to create a span. So what we can see here, span 1, 0, 0, 0, 1, 0, that can be considered to some extent a subspace because these are two linearly independent vectors. And then you can make any linear combination out of these vectors. And these two vectors will serve as the basis for that span or that subspace. Okay. And now what is a subspace? Well, a subspace is a space that has identical rules of vector addition and scalar multiplication in relation to another space. And the first space is a subset, or in this case, contained in the second space. Then this first space is a subspace of the second vector space. I know that was very confusing and that sounded very loaded with terminology. So it's really easy to just go ahead and visualize this. So imagine this as just a 2D plane. We have here an x by y axis. You can imagine the first space as this little space of coordinates here in the third section. And then you can imagine space 2 as a circle encompassing all 4 sections. And imagine space 1 as being inside of space 2, and everything you can do to the operations in space 1, you can also do to the operations in space 2. So basically what that means is that space 1 is contained within space 2, or space 1 is a subset of space 2. Therefore, space 1 is a subspace of space 2. Okay. Please see other videos regarding subspace for further discussion on the various properties that you can get out of them. Okay. Now we can use these definitions to determine whether or not V1 and V2 form a basis for the span 1, 0, 0, 0, 1, 0. Okay. So to do this, remember what we require to have a subspace. We need the vectors to be linearly independent, and we need the vectors to be able to produce all of the linear combinations of the vectors within the span 1, 0, 0, or 0, 1, 0. So basically that means that whatever linear combination these two can create, the vectors v1 and v2 have to also create them. So let's tackle the first question. Are v1 and v2 linearly independent? Yes. v1 is 1, 1, 0, and v2 is 1, negative 1, 0, which cannot be written in terms of each other, which is the definition of linear independence. So yes, they are linearly independent. So that satisfies our first requirement. So do they span 1, 0, 0, 0, 1, 0? Yes, they do. Note that the linear combination of v1 and v2 can be constructed to equal either of these two vectors. So for example, we could add these two together to equal this vector, this vector. Or we could take the negative of this vector and the negative of this vector and produce this vector. Or you could use scalars on either of these two vectors to produce any linear combination produced by this vector. So basically, yes, any linear combination can be produced by v1 and v2 that can also be produced by these two vectors right here. Hence, we fulfilled the requirements to be a subspace, therefore this claim is true. All right, now, E. Okay, so claim E. A set of n linearly dependent vectors in Rn can span Rn. Now, remember our definition of span before. So if we note that a set of linearly dependent vectors must consist of vectors that are linear combinations of each other. So remember that when you have a linearly dependent set of vectors, each of those vectors can be written in terms of each other. Therefore, they can span some sort of space that is encompassed by the vectors within that set, but we don't actually know if those vectors can span all dimensions, for example, of Rn. We also don't know if that set contains all of the linear combinations that can be contained in the space of Rn. And the reason for that is because it is linearly dependent, meaning that these vectors are only written as linear combinations of each other. So if there existed some vector from outside of this set that was linearly independent and can be added to another vector to create a some sort of linear combination, right? That linear combination isn't contained within the set because this set is linearly dependent. It can only contain vectors that are dependent upon the other vectors within the set. Therefore, we know that this claim is false, mainly because A, we don't know if all of the vectors in a linearly dependent set can span all of the dimensions of the space Rn, and also because if there exists some linearly independent vector that doesn't exist within the set, then the linear combinations produced by that linearly independent vector is not contained within this set of linearly dependent vectors. So we can evaluate this claim to be false. Okay, now, last one. Okay. So, for all matrices A and B, where A is 5 by 5 and B is 4 by 4, it is always the case that the rank of A is equal to the rank of B. Now, remember from problem 4 what our definition is, of rank. Remember, the definition of rank is the number of linearly independent vectors in a matrix. Now, with this in mind, you can think of a lot of different examples where you can have more linearly dependent vectors in A than in B. So I'm going to bring up an example right here. So one can see this example. We have one linearly independent vector here, one linearly independent vector here, and one linearly independent vector here, which totals up to 3. And then here we have 4 linearly independent vectors. So automatically we know this claim is false, because we can see here a situation where the rank of B is greater than the rank of A, which is the exact opposite of this claim. Okay, so that wraps it up. Thank you for watching. Thank you for dealing with a little bit of the shaky cam. There's a lot of pages to explain these problems. Definitely look at the different properties of subspaces and spaces in order to earn a larger grasp of exactly what each of those things can do. All right, thank you so much.